Hello guys, Dr. Hasbullah here, and in today's video we're gonna do one tutorial question about turbo pumps. Usually for turbo machinery problems or examination questions, you will be presented with many inputs. I mean that you will have many values that will be given to you. So it's very important for you to take your time and understand what each of these values means. Okay, and for our example, what we have here is the inlet and exit condition of a turbo pumps. So basically you have an inlet and you also have outlet condition. And for inlet condition, what you have is beta 1 equal to 44 degree, and then you also have beta 2 which is equal to 30 degrees. Okay, so if you still remember, beta is relative flow angle, right? And next what we have is the R1, which is the radius at inlet, is 21 millimeter, and then radius at outlet is 66 millimeter. Usually when radius is given, it means that you are required to find the velocity of the blade, because the rotational velocity multiplied with the radius will give you the blade speed. Next, what you have is the blade thickness at inlet is 11 millimeter and the blade thickness at outlet is 5 millimeter. And additional information that you have is that rotational velocity is 2500 revolution per minute, and you also have a condition that is called no pre-rotation. Now the meaning of pre-rotation or no pre-rotation, it means that at inlet, the absolute flow angle is 90 degrees. Okay, and you will see this when we draw the velocity triangle later. Now, what does the question want? Okay, because the question gave you many inputs, many values, so usually the question will also expect you to produce many calculations or many outputs. So in this specific tutorial, what the question wants is, first is the discharge. Okay, and discharge is Q or volume flow rate, right? And then it also looks for theoretical head, which is HT. Okay, and then it also looks for the required power, and the required power is W dot P, and next it's looking for the delta P or pressure difference or pressure rise across the impeller. Okay, and we know that this is P2 minus P1, and well, we're gonna solve this using Bernoulli equation or energy equation later. Alright, and the second thing that the question wants you to find is the theoretical head discharge curve. Okay, let me write it here. So this is the theoretical head discharge curve. This question means that you need to find the relationship of HT and Q. Okay, we've done this before and we will find this later. Now let's try and solve the question number 1, which is discharge, theoretical head, required power, and delta P. Now the key for any turbo machinery equation, particularly the pumps and turbines that you're going to learn later, is to find out what is the velocity triangle looks like. Okay, preferably you will need to find all the velocities in the velocity triangle and also figure out what are the angles, the absolute flow angle and relative flow angles inside the triangle. Once you have that, you basically can solve anything that the question wants you to solve. So now why don't we try and construct our velocity triangle for inlet and exit of the pump. Now for velocity triangle, I'm gonna use purple, right? Now let's figure out the velocity triangle. How does it look like at inlet? Alright, so we know that one condition at inlet that is very significant in the construction of velocity triangle is this condition, right? The alpha 1 is 90 degrees. So there are 3 components in the velocity triangle. First is the blade velocity, that is U1. The second component is absolute velocity. This is capital V1. And the final component is the relative velocity. This is the V1 small. Okay, and this is your alpha, right? this is your alpha, which is let me label it here. So this is your alpha, which is equal to 90 degrees. This is alpha 1, and we know that beta 1 here is 44 degrees, and beta is the relative low angle, which is the angle between relative velocity and the blade speed. So beta 44 is actually here, right? So beta 1 is 44 degrees. I think you can see it. You have the rotational speed and you have the radius and inlet. So you can easily find U1, right? But we will find it later, okay? But we need to construct the velocity triangle for exit first, and let's see how it looks like, right? And for exit, what you have is quite similar still. 3 components. So you have the U2, okay? So U is still heading to the left. If we are assuming that this wheel or this impeller is rotating clockwise. And this is your U2. And next you have the relative velocity at exit. Okay, this is the small v2, right? And then you have the absolute velocity at exit, which is the capital V2. And let's draw this line here that is perpendicular to the blade velocity. This is 90 degrees. And we know that we have something that is beta 2 equal to 30 degrees. And beta 2 is the angle between the relative velocity and blade speed. So this is your beta 2. And this is equal to 30 degrees. And I'm going to label here is alpha 2. We don't know what alpha 2 yet. Okay, and we don't know what U1 yet, and we don't know what U2 yet. Okay, so why don't we try and find U1 at the moment? Okay, so U1 is going to be omega times R1. And omega is simply 2 pi n divided by 60 times R1. Okay, and let me change the color to black. Alright, so now n is 2500, so this is 2 pi 2500 divided by 60 times R1, and R1 is 21 millimeter. So this is 0.021, and this is equal to 2 pi times 2500 divided by 60 multiplied by 0.021, 5.5 meter per second. So I'm going to label it here. This is 5.5 meter per second. Now that we have U1, I think for similar strategy, we're going to use it to find U2, right? So U2 is omega R2. This is 2 pi n divided by 60 times R2, and R2 is 66 millimeter. So this is 0.066. This is equal to, remember n is 2500. And this is 17.28 meter per second. And I'm just going to label it here. This is 17.28 meter per second. Okay, now that we have U1 and U2, okay, we are actually almost completing the triangle. If you notice, for the inlet triangle, okay, for the inlet triangle, you basically now, using trigonometrics, you can actually find the velocities for V1 and small v. Right? Because you have the angle and you have the U1. Right? So just using trigonometry, you can actually complete this triangle. But at exit, you need to find some things first before you can complete the velocities and the angles for exit. Right? So what we are going to do now is we're going to take a look again at the question. What does the question really want? Okay? First, you are looking for the discharge or Q. Okay? And the volume flow rate, we've done this before. So V times area. So velocity will be the velocity that is perpendicular to the blade speed. So this is Vn1, and area at inlet is 2 pi R1B1. Right? And if you want to use exit to find the Q, it is simply Vn2 times 2 pi R2B2. Okay, and based on what we know so far, I think we can safely say that we already know everything, right? We know 2 and we know pi, we know R1, and we also know B1. But the thing that we don't know yet is Vn1, okay? So where is Vn1? So Vn1 is the absolute velocity that is perpendicular to the blade speed. But if you look at our inlet velocity triangle here, and if I use green to mark it, This is also your Vn1. So V1 is actually Vn1. Okay, because this is already perpendicular to the blade speed. Right, so now how do we find Vn1? Now it's quite simple, right? Because you can use the tangent relationship and using this angle. So tangent beta 1 is actually Vn1 divided by U1. And we know that U1 is 5.5 and beta 1 is 44. So your Vn1 is 5.5 tangent 44. This is 5.31 meter per second. Let me write it here. This is 5.31 meter per second. Right? And once you know this, let's plug it in here. Okay, so Q is Vn1 2 pi R1 B1. So this is 5.31 meter per second times 2 pi. What is the radius at 1 is 21 millimeter and B1 is 11 millimeter. I believe that this is 11 millimeter. Okay, so this is 0.021 times 0.011 and you will end up with Q of, this is 7.707 times 10 to the power of minus 3. The unit will be meter cube per second. Okay, so basically you already have the answer for this question. Okay, now the second part of the question is looking for theoretical head. Let's find out where are the equations for our theoretical head before. Okay, so this is it, I think. So HT is equal to U2 V2 cos alpha 2 divided by G. Alright, so if I write it again here, HT is equal to U2 V2 cos alpha 2 divided by G. Right, now here is the interesting bit. Okay, we already know what is U2. Now what we need to find is V2 and alpha 2. Okay, now let's take a look again at our velocity triangle here. Right, so we are looking for V2 and alpha 2. Okay, so if you remember, we already found the Q, which is the volume flow rate or the discharge. And for the discharge, if we are looking for the discharge at exit, we can use this equation where we know R2 and B2, and what we don't know now is Vn2. Where is Vn2? Vn2 is here, Vn2. Okay, and because now we already know the flow rate, of course the flow rate at inlet will be similar with the flow rate at exit. Now we can find the Vn2. Okay, now we are trying to complete the puzzle. We are trying to complete the puzzle for the second velocity triangle. Okay, now Vn2, using this equation, so Q is, let me use black, right? So Q is 7.71 times 10 to the power of minus 3 is equal to Vn2 times 2 pi R2 B2. Okay, so Vn2 is 7.71 times 10 to the power of minus 3 divided by 2 pi. R2 is 66 millimeter and B2 is 5 millimeter. So this is 0.066. This is 0.005. Okay, and you end up with Vn2 equal to 3.72 meter per second. And in here, I'm just going to label it. This is 3.72 meter per second. Okay, now what do we do with this information? Okay, basically what I'm looking for is this distance. Okay, because when I find that distance, I can actually find this distance. Right? And when I have this distance and this value, I can find V2 and I can find alpha 2. Does it make sense to you? And this distance is VT2. Okay, we know that the total length of this distance is U2, right? And U2 is 17.28 meter per second. Okay, and now that I have beta 2 equal to 30 degrees and I have this information, I can actually find this distance. Okay, so that distance, I'm going to call it x. Okay, x. So to find x, what I can do now is I'm going to take the tangent of beta 2. Okay, this is equal to 3.72 over x. Okay, and if I want to find x, x is 3.72 divided by tangent of 30. Okay, so I'm going to have x equal to 6.44 meter per second. Is that right? Okay, so this is 6.44. And to find this distance, this is actually 17.28 minus 6.44, which is equal to 17.28 minus 6.44, which is equal to 10.84. Okay, so I'm just gonna replace the value here. This is 10.84. Does it make sense? Right? So now you have 10.84 for this component of triangle, and you have 3.72 for this component. Okay, now because this is 90 degrees, you can actually now find alpha 2, and you can also find V2. That's how you do it. So alpha 2, let me write this in another color. So let's do pink here. So alpha 2, if I do tangent alpha 2 is equal to 3.72 divided by 10.84. So I'm going to have alpha 2 equal to 18.9 degrees. Okay, if I label it here, this is 18.9 degrees. Okay, and I can also find V2, right? So V2 is 10.84 square plus 3.72 square root everything. So that's going to be 10.84 square plus 3.72 square root of everything. This is 11.46 meter per second. So V2 is 11.46 meter per second. Alright, now I think we have everything, right? We have alpha 2 and we have V2. Okay, now can we find our theoretical head now, right? Of course we can. So this is now, let me change this to black. This is now, U2 is 17.28 and V2 is 11.46. Cos alpha 2 is 18.9 divided by 9.81. Right, so my HT, sorry, this is actually HT, yes, theoretical head, right? So my HT is, so my HT would be 19.1 meter. The unit for HT is meter. So that's it, guys. Our second answer for the question, right? So now this is done, and now we have also done this HT. Okay, now that we have the discharge and theoretical head, we need to find the required power, that is W dot P. Now I believe that we have almost completed our velocity triangle. So any question that comes after this, we can easily solve it as long as you know the equation. Now let's find the equation for the required power. I believe we have it somewhere here, and I think this is the equation that we were looking for, except this time we were using P, alright, but this is a required power, or now we are using W dot P. Okay, so W dot P is equal to rho GQ HT, and fortunately for us, we know rho GQ and also HT. So what's left to do is just to plug everything into the equation, and we are done for this question. So W dot P is rho GQ times HT. So this is 1000 times 9.81 times Q is 7.71 times 10 to the power of minus 3 times HT is 19.1. Okay, and this is equal to, this is 1444.6 watt. Okay, so this is the required power for the pump to operate, right? And let me write this in red. And now, going back to the list of questions. So, of course, we've done this. We've done the second one. We've done the third one. And now, we are looking for the delta P. Delta P is the pressure difference between the inlet and the exit of the impeller, right? We know that pump, the purpose of pump is to increase the pressure. Right, so of course the exit of the pump P2 will be higher than P1. Right, now we are looking for that difference. Okay, now to solve for this, I would like to go back to the original energy equation. Okay, which is this one. Okay, so for energy equation, let's write the balance first. Okay, so in energy equation, what you have is P over rho G plus V1 square over 2G plus Z1 equal to, this is P1, this is P2 over rho G plus V2 square over 2G plus Z2. Okay, and when you have a device that is adding energy to the fluid, right? A pump adds energy to the fluid, right? A turbine extracts energy from the fluids. Okay, but for pump, when it adds energy to the fluid, you need to add HT on the left hand side. Okay, so your HT is here. Okay, and because impeller is quite small, so Z1 and Z2 is usually at the same level, or you can actually neglect it, okay, relative to the overall equation. Now, can you find P2 minus P1? Of course you can. So this is now P2 minus P1 divided by rho G is equal to HT plus V1 square minus V2 square over 2G, right? And our HT is 19.1, if I'm not mistaken. That's right, 19.1 plus, what is our V1? Okay, our V1 is VN1, which is 5.31. This is 5.31 square minus, and our V2 is 11.46. This is 11.46 square over 2G. Alright, and let's see. This is 13.8. Okay, so P2 minus P1 is 13.8 times rho G. Rho G is 9810. Okay, so P2 minus P1 would equal to 135.8 kilopascal. Alright, and there you go. This is the answer for the fourth question. Okay, you're on fire now, guys. So what you have done now is we have question 1, question 2, question 3, and question 4. Okay, and finally, we are to find the theoretical head discharge curve. Alright, and for this we need the equation as usual. Okay, and this is our equation for the curve. Okay, so you have the HT and you have the Q. You want the relationship of HT in terms of Q, right? So now, this is quite a long equation. So what I'm going to do is I'm going to copy this and paste it down here as our reference. Okay, and then this. Okay, so that is your HT, and if you notice, we have everything we need. Okay, and now let's plug in all the equation with the numbers. So what is our omega? I believe we did not calculate the omega. So omega is 2 pi n divided by 60. So this is 2 pi times 2500 divided by 60. This is 261.8. Okay, so this is 261.8 radian per second. So 261.8 square times R2 square. R2 is 66 millimeter. 0.066 square divided by 9.81 minus omega is 261.8 cotangent. Beta 2 is 30 degrees. divided by 2 pi B2 is 5 millimeter, 0.005 times G, 9.81. This is Q. Okay, let's solve this. This is 1471.3 Q. Okay, and what you need to do now is just to plot the graph of HT versus Q. Okay, so if I do this carefully, and this is HT, and this is Q, we know that the graph is linear with a negative slope, and it's going to intersect here at y-axis at 30.43, and let's find out where it's going to intersect at x-axis. So given HT, if HT equal to 0, then Q becomes 30.43 divided by 1471.3. It's going to intersect at about 0.02. This is 0.01, and the graph will look something like this. Okay, but just to find out where is our operating condition, what is our HT just now? So our HT is 19.1. So 19.1 is about 20. Okay, so this is it. This is 19.1. And what is our Q? Okay, so Q is 7.7 times 10 to the power of minus 3. So that could be 0.01, right? Quite close to 0.01. So just a bit before 0.01. Okay, so that will be your intersection. So this is 7.71 times 10 to the power of minus 3. Okay, and this is 19.1. And this is our operating condition. This is our specific operating condition. And as you notice here, the operating condition falls onto the theoretical head discharge curve. Okay, so basically this is your answer, right? So this is your answer for question number 2. So you've done a lot here, right? You've got the discharge, you've got the theoretical head, required power and delta P, and you also have the discharge curve, right? So please try and do this tutorial again and again and relate what we've been doing now with the equation that you've derived in the previous lesson. Okay, because whatever the equation that you've derived, you're going to use it here. Also remember that the key is actually the velocity triangle itself. If you can master the technique of drawing the velocity triangle, you can find any answer for any questions. So that's it for this video, guys. I'll talk to you soon. Bye.